Uh, yeah, okay. So, yeah, thanks, Eric, for inviting me. We've had a lot of wonderful talks in the mini symposium already. And I think Carlos' talk right at the start has a fairly large intersection with what I'll be speaking about today. But because most of the talks have been more on like the technical, mathematical oriented side, I'll maybe try to keep things a little uh, more accessible at a broader level. So I'll also be talking about pulse coupled neurons, similar kind of model that we mentioned earlier. And I just want to mention that this is work I've done with Tom Antonsen, Michelle Gervin, and Ed Ott. And I also want to just thank David Hathcock and Kimberly Crane, who are two summer undergrad students. So let's just get started with some motivation. Brain's a network of neurons. We all know that for sure. So you have a neuron that is a very unidirectional thing. You have one neuron connected to another neuron, and you have some kind of electrical pulse that goes in one direction and then is conveyed to the next neuron via a synapse. So it's very much a directed network of neurons in the brain. And you would want to have some kind of mathematical modeling perspective to be able to understand brain function. But obviously, the number of neurons in the brain is actually very, very large. And you would want some kind of reduced system of equations to actually model what's going on. Now, I'm obviously not claiming that I'm going to actually be accessing anything at the level of the full brain, but just in terms of motivation, we want to be able to have some sort of reduced system description. So in particular, I won't be talking about all neurons, but I'll be talking about one particular type of neuron. So in the late 1940s, Hodgkin had come up with a classification of neurons, and he had basically described these neuron dynamics with regards to their response to like an electrical impulse. So I give like an injected current via some sort of step function, and he came up with three classes of neural excitability on the basis of what the neuron does given this injected current. So I'll particularly be focusing on class 1 excitability, which is the kind you find in the visual cortex, for example, where for different amounts of injected current, you basically see different kind of spiking behavior. And you can look at the firing frequency as a function of the injected current, and you basically see that you have this kind of bifurcation, and you have this, you can have arbitrary low firing frequencies depending on the amount of injected current that you give. So there's a kind of neurons that we're interested in modeling, and all this can be modeled very well via the theta neuron model, which is something that was introduced by Carlo in his first talk in the symposium. So the model is very simple. You're describing the entire state of a neuron via phase angle theta, and you just have this one parameter eta over here that controls the excitability of this neuron. So to give you a feel for what the dynamics look like, when eta is less than 0, you have these two kind of fixed points on the circle. You can think of a resting state and a spiking threshold. So for small perturbations, you just come back, whereas for large perturbations, you go all the way around the circle, and then you come back. And whenever we cross theta equal to pi, we said that this neuron has spiked. Okay. And then as eta goes to 0, these two fixed points merge, and you basically have this kind of saddle node bifurcation and invariant cycle, or a snake bifurcation. And for eta larger than 0, then you have this periodic spiking, right? So just looking at this eta larger than 0 case for a moment again. So what we're basically saying is that you have these two neurons, you have some synapse over here, and as my state of the neuron varies like this, I'm going to assume that I have some kind of chemical signal that's emitted that varies as a function of theta, which peaks at theta equal to pi, which is basically why I'm saying that theta equal to pi corresponds to the net neuron spiking. So I'll represent this via some q of theta. And then if I look at the dynamics of q of theta as a function of time, I basically have this periodic spiking where the frequency of the spiking is controlled by the size of eta. So you can have arbitrarily low spiking, arbitrarily slow spiking, which is basically the kind of neural classification that Hodgkin was interested in when he was talking about the kinds of neurons you can see. Okay, so this is just one neuron, but in this symposium, we're obviously not interested in just one neuron. We're interested in networks of these neurons. So the way I have the network-based coupling is something that you had seen a little while earlier. I'm basically adding like a synaptic coupling term in the eta sub i's. So I'm just adding up these chemical signals that I get from all of my other connected neurons. And over here, A is just my network adjacency matrix, K is my coupling strength. I'm just scaling things by the average degree of the network. or the average number of connections per neuron. And my eta sub i's are my intrinsic excitability parameters. And I'm drawing them from a Lorentzian, which, if you've been looking at the other talks so far, you know the kind of dimensionality reduction I'll be talking about very soon. So I have this nice Lorentzian distribution of the eta sub i's, which will help me do the analysis with the auto-intensive method later. Okay. So a few comments on network topology. So before our work, I mean, most previous work on networks of theta neurons was generally restricted to few classes of network topologies. Either you had like two populations, or you had like a ring, or you had an all-to-all coupled systems. Obviously, since our work, there have been more papers, such as the paper that Carlo was talking about, where they have looked at more kinds of general network topologies. But that's basically what we wanted to achieve when we were looking at this work, where we wanted to be able to talk about more general network topologies than just something like an all-to-all coupled system or just a ring of oscillators. And that's actually going to be quite important, because you do see dynamics that do heavily depend on the form of network topologies, and they do depend a lot on the heterogeneity of the network structure in these systems. So our main focus will be networks with heavy tail degree distributions, which is biologically relevant. There have been studies that indicate that if you look at the connectivity in the brain, you do actually have heavy tail degree distributions. So for our modeling perspective, we're going to use independent, identical, truncated power law distributions for the in and out degrees. And in particular, we'll be looking at, whenever I'm talking about full system simulation on these finite size networks, I'm looking at around 5,000 neurons with a power law distribution with a power law exponent of about 3. Okay. Now, beyond just the degree distribution, as we had seen a little while earlier, the network assortativity is also going to be important. So for those of you who weren't there earlier, just to give you a brief overview of what network assortativity is, it's basically a measure of degree correlations across edges. So you generally look at it via some sort of Pearson assortativity coefficient, and you have assortative networks, which are nodes with similar degrees preferentially connected, and disassortative networks are nodes with dissimilar degrees preferentially connected. And like a neutral assortativity is just like a random Erdős-Rényi network, where I'm just randomly throwing the edges onto my network. So this is just a quick picture of what these kind of things look like. And this picture and this description I've given you so far is very much for an undirected network, but just using the terminology that was mentioned earlier in this session, what I'll be talking about will primarily focus on in-out degree assortativity. So I'm looking at the in degree of a node and its correlation to the out degree of neighboring nodes. And once again, this is a biologically relevant quantity. There have been experiments that say that in like human brain studies, you have an assortativity of around 0.15 to 0.3. So that's like the kind of values that would be reasonable to look at or that we might be interested in. Okay, so to describe the dynamics using an order parameter, just the average of all the phases, you've seen this several times so far, just a helpful quantity that characterizes the amount of synchrony in the system. If my phases are all spread out, I have a small order parameter. If I have a high amount of synchrony, or I just have all the neurons are doing similar things, I have a large magnitude of R. And if my neurons are all spiking together, I'll be able to see that in my R as well. So it's just a useful quantity. And you can also define a degree dependent order parameter, which is just, I look at the average of all phases over neurons that have a certain given in and out degree. That'll just help me look at the degree dependent behavior in my system. Okay, so what can we then simulate? You know, what is in terms of feasibility for like a simulation of this network? So you could do like a simulation of the full system, but that's going to be slow and noisy. So this is just an example of a simulation on 5,000 neurons. And this is, I'm just showing you what the order parameter looks like. This black curve over here is just the unit circle, which constrains my order parameter. It will always lie within the unit circle. And you have this noisy blob over here of dynamics. Whereas if you can write a reduced system of equations, then you can show that you have this wonderful, perfect, just this one fixed point, which easily captures what you're seeing in this much larger simulation. And indeed, if you do go to larger and larger number of neurons, you do approach this fixed point more and more tightly. So it's really wonderful that you can just might have a means to be able to get this fixed point directly. So how do we go about doing that? So we are going to look at the limit of infinite network size. So this does have the limitations of the finite size effects that we've heard of in the previous two talks. But just keeping that aside for now, we will be looking at the infinite network size limit. So, as you generally do for the Otto-Anderson method, you assume that there's some distribution of these oscillators in terms of their phase angle for a given excitability parameter for neurons with a particular in and out degree as a function of time. And instead of coupling of individual nodes via individual edges in the network, we assume a mean field hypothesis. So given a particular degree distribution and given a particular form of the network assortativity, I'm just going to assume that my network is like a typical member of that ensemble of networks under the constraint of the distribution and the assortativity. And when you do that, and then you can basically go to like a continuum limit and write the dynamics of this complicated system of ODEs in terms of this one PDE, which is just a flow of this distribution. And yeah, PDEs are no fun, at least not for me, but you can then use the Otto-Anderson method, which basically looked at these large systems of phase oscillators and was, some work by Restrepo and Ott in 2014 had introduced network-based coupling via the Otto-Anderson ansatz. So we just extended those ideas towards these theta neuron models. We've had a lot of talk about the Otto-Anderson ansatz, but there hasn't been too much detail about how you actually go about doing it. So I'll just give you like a one-slide overview of what you actually do for those of you who may not be too familiar with it. So you have basically this flow over here of the distribution F. And the idea is that you assume that you can write this F distribution in terms of some arbitrary quantity B of eta, D, T in the kind of following form. So this is just an assumption that you're making. This is the ansatz of the Otto-Anderson ansatz. And you're basically describing a manifold, which then turns out to be an invariant manifold. So this G over here is just the assumed Lorentzian distribution that I had assumed for the eta sub i's. And the idea is that when you plug F into this equation over here, you see that this form of F is invariant. And you can, instead of describing the dynamics of F, you can see that you just need to describe the dynamics of this B instead. And then you can integrate out the etas to obtain a system of the B hats. And this integration out becomes quite simple because of the Lorentzian assumption. And this integral actually is just going to be equivalent to this integral, which is just the degree-dependent order parameter. So just to summarize, I mean, what the Otto-Anderson method in this particular situation is letting you do is that you started off with this network-based coupling of theta neurons, and you then obtain a system of equations for the degree-dependent order parameters. So this does give you improved computational complexity. In the full system of equations, you have some n equations, and you have order of n times the average degree of operations at each time step. In the reduced system of equations, you obtain one equation for each degree-dependent order parameter, which, very similar to what Carlo had earlier, you have the number of equations corresponding to the number of degrees in the support of the distribution. So you have order of m sub d operations at each time step, but you can do this kind of degree clumping. So basically, you can look at the function. What you observe is that the dynamics of nodes of a particular degree appear to be similar for nodes with similar degrees. So if that is true, then you can just interpolate for intermediate values of degree, and you can just use a much smaller number of degrees and then interpolate the rest and still obtain a very, very accurate picture of the dynamics of the system that are going on. And in fact, when you have networks with neutral assortativity, it turns out there's a trivial dependence on the out degree in the system of equations. So you can have an even more significant reduction in the computational complexity of this system of equations of the degree-dependent order parameters. Okay, so that just tells you about the kind of reduction method that we're using. So what kind of system dynamics do we see? So once you have this reduced equations, you can have a very efficient characterization of the system dynamics. And for these theta neurons, we basically see them existing in three phases. You can have a partially resting phase, you can have an asynchronously firing phase, or you can have a synchronously firing phase. So I won't go into too much detail of like an entire phase diagram, but let's just give you some kind of intuition for what these dynamics present themselves as. So I'm just looking at this kind of a parameter range right now. So this means that I broadly have neurons that are in like a resting state. So in this case, what I see for a low value of the coupling strength, my order parameter lies over here, very close to the edge of the circle, and it's just at a fixed point, which just means that most of my neurons are just in the vicinity over here, and they're all just at fixed points themselves. So if I just plot out the dynamics of individual neurons, they're all basically at fixed points as a function of time. And then as I increase my coupling strength, I move away from the edge of the circle, my order parameter moves away from the edge of the circle, and some of my neurons begin to start to fire. But you still have some fraction that are still at fixed points. And then eventually, oh yeah, and so these are what we call the partially resting phase, where you basically have some fraction of the neurons that are still resting, and you have these fixed point of the dynamics that are close to the edge of the circle. But then eventually, when I increase my coupling strength even further, I eventually go to an asynchronously firing phase, where basically all of my neurons have started to spike, and my order parameter has moved much away from the edge of the circle over here. And so you can see clearly that all the neurons are firing, but they're asynchronously firing because the order parameter is still just a fixed point. So my phases are all just spread out on the circle, and it's just a fixed point, so I don't really have any synchrony in my firing that's going on. Okay, so just a quick comment about this partially resting phase. One might ask which neurons are firing and which neurons are not. And what's interesting is that you see like this kind of degree-dependent behavior that pops up. So I'm just plotting the degree-dependent order parameter as a function of the in degree. So for small values of the in degree, you see that you have a high value of the degree-dependent order parameter, which over here corresponds to these neurons that are in the resting phase. And the ones with larger in degree seem to be the ones that are spiking, which kind of makes sense. These ones are receiving signals from much more neurons, so they cross that spiking threshold more easily, so they're more likely to spike. But it's nice that, via this kind of a description, you can look at degree-dependent behavior, which you can't really see until you can actually have a systematic way of describing the network-based dynamics of these systems. Okay, so, and then we can also look at the transitions from the partially resting phase to the asynchronously firing phase. You see this kind of transition that happens mediated by this hysteresis. And I just want to point out that you can calculate the fixed points explicitly via like the reduced system of equations. And you can also do a full network simulation, which is much, much slower in terms of computational runtime, but it all obviously matches extremely well. So these are networks with 5,000 neurons, and they are itself already quite close to the infinite size limit. And if you're talking about any kind of neuronal context, so you're interested in actually looking at, say, small modules of the brain, 5,000 neurons is certainly a very small number. So that does tell us that just looking at the infinite size limit and the Otto-Anderson analysis is actually going to be useful for these kind of biologically relevant systems. So basically over here, you have this partially resting phase, and over here you have the asynchronously firing phase. As you increase the coupling constant, and this transition is mediated by a hysteresis. Okay. You also can see limit cycles in the order parameter dynamics. So this basically corresponds to like a synchronously firing phase. So not only are my neurons firing, but they also have some amount of synchrony when they're going around the circle. So you have a synchronous firing. And this is for the case of heavy tail degree distributions. But what's interesting is that if you look at different kinds of degree distributions, you see a quite different structure to this limit cycle, which just tell you that being able to model the particular aspects of network topology is going to be quite important for really understanding what goes on in these systems. And I just want to say some brief comments on the effects of assortativity. There's something which was mentioned in a fair amount of detail in the first talk by Carlo. But the idea is that, so just to remind you, assortativity is like a measure of degree correlations across edges. And what we saw is that just small amounts of assortativity or disassortativity could significantly alter the qualitative behavior of the network. So if I have the middle panel over here is a network with neutral assortativity, R equal to 0, where you have a limit cycle behavior where you have synchronously firing. introducing a small amount of assortativity or disassortativity did make you go through a bifurcation, which led to an asynchronous firing phase. So in that sense, it certainly is quite important to keep in mind that looking at network topologies is not going to be sufficient. You do also need to be able to look at the network assortativity. And this is especially important because assortativity is a biologically relevant quantity. And you can see that changes in the assortativity on the level of the biologically relevant values does indeed lead to different dynamics. So when it comes to actual system modeling, it's going to be important to have a formalism to be able to take this into account. So with that, I'd just like to conclude. So the auto-random ansatz is a useful technique for obtaining descriptions with significantly lower dimensionality. And these dimensional reduction methods give you significant improvement in the computational efficiency. And our main result is that the network topology are important effects in networks of theta neurons. And this is true not just for the degree distribution, but also for the network assortativity. And this is the references. Just like to thank you all. And the details of everything that I've spoken today can be found in this paper of ours from a couple of years ago. Thank you.
Thanks a lot, Sarthak, for this really interesting talk. There is time for questions, and I can see there's already one question by Jordan. I'll switch to the live mode. Jordan, can you hear us? And can we hear you? No?
So I can just read out the question.
Okay, sure.
Jordan, the question was, what do the reduced equations look like, and what can be said of finite size effects? So I don't have a slide for exactly what the reduced equations look like. If I just really give you some sort of feel for, so this is what the finite system of equations look like. And so when you plug this in, basically what you need to do is you basically look at a continuum version of this kind of summation term over here, which accounts for network-based coupling. So what you end up seeing is you have a reduced system of equations which looks very much like the globally coupled theta neuron model, which has an equation that looks somewhat similar to a single neuron itself, plus a sort of term that allows for this coupling in terms of the assortativity function. So you need to, so at least in our formalism, we need to assume some sort of assortativity function, which is like the probability of a node with particular degree connecting to a node with another degree. So you have that function that gets thrown into the mix, and you have an equation that looks somewhat like this, but in terms of a complex system, something like how a general auto-Anderson reduced equation looks like, with the coupling term in terms of this kind of assortativity function. I'm sorry, I don't have that equation with me over here right now. The other thing that Jordan was also asking is what can be said about finite size effects. That is a great question. I did not spend too much time looking at that, so I'm afraid I don't have too much to say about that. But that certainly would be interesting to look at via the kinds of approaches that were described in the previous two talks in this session. But we didn't really end up having much time to look at the finite network size effects.
Okay, thank you for this question. Are there any other questions? There is still time. Okay, so maybe there are no further questions right now, but please, if you have any questions that come to your mind to Sarthak or any of the other speakers, go ahead and write an email to them.
Yeah, I would be happy to have additional discussions on email with anyone.
Great. So let's thank Sarthak again, and I'll use my collectively synchronized clapping again for the photos. And I would like to close the session again by thanking everyone for attending, and in particular for all the speakers who did a great job and have shared some wonderful work and given some great talks.